Everyone in this talk, and I am Rakesh Mohan Das. I am a assistant professor in Kalinga Institute of Industrial Technology, Bhubaneswar. I really am glad that I have been given this opportunity to chair this session. The talk is by Dr. Graeme Smith. So, yeah, about Dr. Smith, he is an associate professor at University of Colorado Boulder. He spent a few years in the IBM as a research staff member where he worked on computation and communication in noisy settings, quantum Shannon theory, coding theory, cryptography, geometry and packing, quantum devices, quantum estimation and detection, optical communication, physics of information. His current research interest lies in the area of identifying the fundamental limits that physics places on communication, information processing and sensing, finding new ways to think about information and computation, and new ideas for analyzing them. And the title of his topic today is the theory of quantum information, channels, capacities, and all that. So over to you, Dr. Smith.
Thank you very much. Thank you very much, Professor Das. I'm grateful for the opportunity to tell you about one of my favorite topics, the theory of quantum information, and more specifically, Shannon theory. The quantum Shannon theory. I have, this may be my last talk associated with the University of Colorado Boulder and JILA. As of July 1st, I'll be moving to Canada and joining the Institute for Quantum Computation. And I would like to encourage you to have all of your great students apply there and come do PhDs. There are plenty of great people to work with there.
Definitely.
Great. So, so information theory is kind of, well, it's one of my favorite topics, and it's the topic of the talk today. And basically the idea of information theory, it's about sending and storing and processing data, usually using some kind of noisy resources to try to simulate noiseless resources. So for instance, can you see my cursor?
Yeah, pretty much.
Okay, great. Okay, so on the left here, I can even change it like this. On the left here, we imagine two parties who share some noisy quantum state who try to extract pure state entanglement out of that noisy state. So they're simulating having a perfect noiseless state by doing a distillation protocol. You might be interested in just sending qubits over some noisy medium in a way that the receiver can actually recover the initial encoded qubit state. Very much like what in Shannon's original paper on information theory looked at doing for classical information. It also, we'll talk a little bit towards the end of the talk of the theory of quantum networks. There are all sorts of interesting effects that happen in both classical and quantum network information theory. And for me, my favorite, you can think of information theory from a lot of angles, but for me, the philosophy of this is really, it's about trying to understand quantum mechanics itself. So, one of the goals is to kind of abstract away as much as possible, as much of the detail as possible in your calculations and your considerations, and what's left, what you can't get rid of, reveals what the fundamental limits nature is putting on information processing are. The details that are left also can give us a clearer picture of quantum mechanics, and they can help us understand more traditional areas of physics. And furthermore, the strategies for approaching fundamental limits, they might be realizable either today or in the future. So by pursuing the fundamental limits of practical technologies, we can learn about the fundamental nature of quantum theory without even needing to realize those technologies. Although it's very exciting what people have been doing in recent years in realizing those technologies. So it's, to me, I'm in a physics department. I'm moving to a math department. I don't feel so strongly attached to physics or math. What I do is quantum information, and it's about physics, but all sorts of other stuff like geometry, computer science, engineering, math. And the difference between classical and quantum information theory that I see and that makes quantum information theory very exciting to me is that in the quantum case, there's way more resources and all sorts of interesting interactions between the resources. And that's going to be a theme in what I talk about in my presentation today. So the basic kinds of questions that we ask are, what are the resources in this theory of quantum information? How can we convert them into other more useful forms? How do they interact with each other? And what's the recipe that lets us combine different resources in ways that are fruitful for achieving our goals? So over here on the right, I have one of my favorite books. The title is Flour, Water, Salt, Yeast. Not only is that the title, that's also the recipe for bread. But there's a whole book here about how to cook bread. And the reason you need a whole book is that actually there's a lot of different ways you can combine those resources. And what you get out at the output is very dependent on how the details of how you do those interactions. Maybe a more conventional, like physicsy recipe is this recipe here for teleportation. Teleportation is a protocol that takes two very different resources, entanglement and classical communication, and puts them together in a way that lets you get something that neither one of them would let you get on its own. If you put them together in just the right way, you can send a quantum state from one place to another. Even though entanglement's not sufficient to do that, nor is classical communication. Together, if you use them just right, you can send a quantum state. And discovering these kinds of recipes in the theory of quantum information and ways to combine these different resources is one of the motivating goals in quantum information. So here's just an outline of the rest of the talk. I'll talk a little bit about information theory basics, like a 10-minute course on what information theory is, and then we'll look at quantum channels and quantum capacities and how adding quantum theory to information theory gives us new complications and new possibilities in the theory. And specifically, we'll look at additivity and non-additivity in the theory of quantum information, and some very strong interactions that you can get between different resources in the form of superactivation. And finally, I'll talk a little bit about quantum networks, again, where we can combine two very different resources to get an enhancement in network performance by using those two resources judiciously. Oh, there we are. So let's look at information theory. Well, the basic quantity in information theory is the capacity of a channel for sending information. And the setting that we're imagining, or that we typically imagine, is we have some noisy process N that takes some input and gives some corrupted version of the input at the output. And we have many independent and identically distributed copies of it. And we'd like to find a way to take that noisy resource and use it to send a message, M, over from sender to receiver in such a way that with high probability, the received message is the intended message. And we do that by encoding our intended message across many uses of the noisy channel in such a way that with high probability, the receiver who gets the outputs of the noisy channel can with high confidence determine what the message sent was. And then the capacity is just defined as, well, what's the best rate you can get for such a code that works? So what's the best number of bits I can send per channel use in the limit of many channel uses across the channel? The best value, that's called the channel capacity. It's kind of a complicated thing though, right? Because it's defined in terms of this asymptotic performance of all possible coding strategies. The kind of magical thing that happens with the channel capacity is that there's a very simple mathematical way to characterize it. Specifically, if I have some transition probabilities, the probability of X getting mapped to input X getting mapped to output Y, the capacity is just given by this clean formula here. It's the maximum correlation you can generate between input and output of the channel with a single use of the channel, where the correlation is measured by this mutual information formula here. And furthermore, the optimal distribution that maximizes this mutual information, it gives you a recipe for capacity achieving codes. Basically, what you should do is you should make your code words look a lot like they were drawn identically from the optimizing distribution in this formula. So what we get, we start with some asymptotic and very operational definition of channel capacity. The beautiful thing is out comes a very simple formula that lets us calculate what's the channel capacity for any particular channel model that you might have in mind. And at the heart of that is additivity. Additivity is kind of, if I had to summarize what happens in the quantum case versus the classical information theory is additive. Quantum information theory tends not to be. What does it mean? It means if I ask, what's the capacity of two different communication links? This is a blue wire, this is a gray wire. The capacity of the joint channel, where you get to use the two of them together, is just equal to the sum of the individual capacities. And that means when you use these two resources, all you should do is just try to use the blue one separately from the gray one, and use it as well as you can, use the gray one as well as you can, and that's the best you can hope for if you have the two things together. They don't interact in any interesting way. Additivity tells us that resources just interact trivially. So in terms of cooking, additivity is kind of, well, a trivial interaction. It's a little bit like making a smoothie. You want your smoothie to taste more like grapes, you add more grapes. There's not much of a fancy chemical reaction going on inside this. It's just mixing all these things up together. Non-additivity is where we have non-trivial interactions between resources. And that's the thing that tends to come up when we're dealing with the quantum theory of information. So for example, when you make bread, the bread that you make isn't particularly, well, it's much tastier than any one of these ingredients on its own. You can't really eat flour. You should cook it. You should mix it properly with water and salt and yeast. So what we find is that in information theory, classical information theory is a lot like making smoothies, and quantum information theory is much more like baking bread. And again, these interactions give us new opportunities for finding new phenomena and better performance than would be possible naively based on classical intuitions. So let me just illustrate how this additivity comes into play in classical information theory. The way you show this nice single letter formula for the classical capacity is first you show that this much more complicated thing characterizes the classical capacity of a classical channel. It's the limit of the maximum mutual information between input and output of many copies of the channel, normalized by how many copies of the channel you have. And if you take this limit as n goes to infinity, that's the capacity. And the sort of the simplifying thing that happens in this case is that this C1, this maximized mutual information, is additive. So actually, when I evaluate it on many copies of the channel, it's just equal to n times the thing evaluated on one copy of the channel. The n's cancel out. You don't need to take the limit, and you just have to consider a single use of the channel. So that's sort of the magical simplification that you get with additivity in the classical setting. And just to get a feel for a particular channel, I'd like to talk about the erasure channel. It's one of the simplest classical channels you can imagine, and there's nice quantum versions of it that are also relatively simple. The basic idea is, well, with some probability p, the channel is going to have an erasure. If there's no erasure, the input gets mapped to the output without any change. Yeah, so it gets mapped faithfully if there's no erasure. If there is an erasure, then the output of the channel just gets an erasure flag, and the receiver doesn't know whether it was a 0 or a 1. They have no information about whether it was a 0 or a 1. They just get a flag that says, sorry, this bit was corrupted. And for this channel, you can evaluate the capacity of the channel. The maximum mutual information is given by this formula. It's just 1 minus the probability of erasure. And that's quite amazing, because with n uses of the channel, that's the setting we're considering, right? With n uses of the channel, you know, p times n, typically what will happen is p times n of the bits that you send will get erased. So that means p times n of the received message, the received bits or the received signals will just be erasure flags. So it's just a pattern of erasures. What's left is 1 minus p times n bits that actually get through. And what this capacity formula says is each one of those bits is informative. You can find a code that makes each one of those bits informative. And you can do that even though you don't know which of the bits are going to get erased when you do your encoding. So you're squeezing an awful lot of information through this erasure channel. And you can see as the erasure probability goes up, you always have some positive capacity unless the erasure probability is all the way up to 1. And again, as I said, this even gives a recipe for making capacity achieving codes. You just choose, for each of your code words, you choose it randomly according to the input distribution that maximizes the mutual information, which in this case is a 50-50 0-1 coin. So that's information theory in a nutshell, or in 10 minutes. Now let's look at what happens when we add quantum stuff into the works. Well, for a long time, back to the 50s and 60s, people knew about quantum mechanics, they knew about information theory, but their main idea was that quantum mechanics is kind of an annoying source of noise in the measurements that you do when you design a receiver. And they thought of it as really nothing, probably a slight wrinkle that we would add to the classical theory. We just need to figure out how to add the quantum noise that quantum effects will introduce. What became more clear in the 80s and 90s is that actually quantum information not only offers us, is not only an annoying source of noise, it also offers us new possibilities for new kinds of protocols and new kinds of things that you can do, and even a better understanding of what information is and how it seats itself in the classical world, and arguably even a better understanding of what it means to be classical, and therefore a deeper understanding of classical information theory itself. So in the quantum setting, there are capacities, again, for our noisy channels. Classically, we have just one capacity, but quantum channels, they have several. They have classical capacities for sending classical information over a quantum channel in a way that the classical information gets received effectively. Private capacity for doing quantum key distribution, basically. You're sending private messages you're sending classical messages over a channel, but you want to make sure that those messages cannot be learned by any party other than the authorized receiver. And finally, there's the quantum capacity. That's the number of qubits per channel use that you can send over a quantum channel. There are also, there's a zoo of capacities, really. I think actually, I think somebody's working on a quantum channel capacity zoo. I'll have to actually look that up again. But there are all sorts of other assisted capacities, like something called the entanglement assisted capacity, or the quantum capacity assisted by classical feedback or two-way classical communication. And each one of them, there's a theory about how do we characterize this capacity for different kinds of quantum channels. I'm going to talk mostly today about the quantum capacity. That's because it's kind of my favorite capacity. It's one where the quantum effects become simplest to observe, but there are similar stories to the ones I'm going to tell about the private and classical capacity, as well as many of the other capacities that are sort of slightly more complicated. So noisy quantum channels, those are kind of the fundamental thing that we're trying to understand. We're trying to understand how can we use a noisy quantum channel to send messages in a way that the receiver definitely gets the message that was intended. So how do we send information noiselessly across a noisy medium? Well, what's a noiseless medium? First of all, a noiseless quantum channel is just a unitary conjugation of a density matrix, basically. And a noisy quantum evolution is very similar to that. You can always just think of any noisy evolution from input to output as a noiseless evolution on a bigger space where the receiver doesn't have access to some part of the space that we call typically the environment of the channel. So if you're a physicist, you can think of an optical fiber and the environmental degrees of freedom. Those are just the degrees of freedom in the fiber that absorb the light, that make sure that whatever light you put in at one end doesn't come out. Well, not all of the light that you put in one end comes out the other end. The degrees of freedom along the way where the light gets absorbed, those are the environment of the channel, and the receiver gets all the rest. And actually, I just wanted to make the point that, in fact, you can always think of a density matrix as coming from entanglement with some inaccessible system, So it's not just that all channels, noisy channels, can be thought of as just unitary interactions with some inaccessible system. If you would like, you can think of all forms of noise and indeed all classical information as being derived from entanglement between different quantum systems. And this way of thinking about it is called the Church of the Larger Hilbert Space. And it's kind of like a very bare bones version of the many worlds interpretation of quantum mechanics. Okay, so what's the quantum capacity? Well, it's defined according to this setting on the left. We have some quantum state psi, and we want to send it we want to encode it so that we can send it across a noisy channel in such a way that a decoder can recover the initial encoded state. And we say the capacity, it's just the maximum number of qubits that you can send faithfully per channel use, or divided by the number of channel uses. So that's given by, that's again, this sort of asymptotic operational definition of what a capacity is. And kind of from a slightly more practical point of view, why do you care? Well, one reason you might care is that this gives us the ultimate limits on quantum error correction. And that's sort of a fundamental topic that we would like to understand much better. There's an answer, there's a partial answer to this quantum channel capacity problem in terms of something called the coherent information. The coherent information we can think of in terms of this Church of the Larger Hilbert Space perspective. If I have a noisy channel from A to B, I can extend it to a unitary on a bigger space, and then I can put in part of an entangled state into the noisy channel and keep around a reference system R. And the coherent information is given by just how much correlation is there between R and the output of the channel compared to R and the environment. And specifically, we look at the difference of the mutual informations. And to make sure it's normalized correctly, we throw a half out in front. And this difference of mutual informations, maybe it shouldn't surprise you too much that it's related to quantum channel capacity, because it tells us something about how much more information goes from the input to the output than the input to the environment. And one feature of quantum information is that it's kind of fundamentally private, in the sense that if you start leaking parts of your quantum information to all sorts of other systems, unless you have control of those systems, you're degrading your quantum information. So it's exactly the stuff that only goes to the receiver. That's the quantum information in the sense of this coherent information formula. And I just wanted to introduce the notation of there's the output of the channel, which we've called N throughout the talk, but there's also something called the complementary channel. That's the environment's view of what the channel is. It's just what you get if you take the channel's unitary, and instead of tracing out the environment of the channel, you keep the environment and you trace out the output of the channel. And in terms of this complementary channel, then the coherent information is really best understood in terms of both the output of the original channel and its complementary channel. So I said this is kind of offering a partial solution to the quantum channel capacity problem. The reason is this coherent information is an achievable rate. What does that mean? It means that if I have a state that gives a certain value of coherent information, then I can achieve that value as a communication rate over the channel in the limit of many channel uses. So we get a similar regularized formula, or multi-letter formula to the one we saw for the classical capacity. The quantum capacity is equal to the limit over many channel uses of how much coherent information can you generate over a single channel, or over many channel uses. And then you normalize it by how many channel uses you got, that gives you the quantum capacity. The problem is this is an optimization over an infinite number of variables now, just like it was in the classical case. But the difference here is that this coherent information is not additive. So we're not going to get the same simplification that we got in the classical case. And that's annoying because it means it's harder to understand the quantum capacity, but it's also exciting because it means we can achieve better codes. We can achieve better rates than you might naively think based on what random coding strategy might give you. So this coherent information gives us the rate that you achieve when you use a random coding strategy. And we can now look at the quantum erasure channel. It's the quantum version of the channel that we looked at before. And the way I like to express it is well, I can express it in two ways, but this unitary expression, I think, is a simpler way to think about it. Basically, well, it maps a qubit on 0 and 1 to a QTrit that's either 0, 1, or an erasure flag. And the way it does that is, well, in terms of the sort of just the output of the channel, with probability P, there's an erasure flag, and with probability 1 minus P, the input state gets mapped faithfully to the output. In terms of this Church of the Larger Hilbert space perspective, you can see what the channel does is it puts, given a state psi, it creates a superposition of the state psi going to the receiver and the environment getting an erasure flag, and the state psi going to the environment and the receiver getting an erasure flag. And the relative weights tell you how much erasure happens. And the quantum capacity of this thing, you can calculate. It's given by 1 minus 2 times the erasure probability. So here I plot it next to the classical capacity of both the classical erasure channel and this quantum erasure channel. That's still given by 1 minus P. But the quantum erasure channel has a quantum capacity of 1 minus 2P. And a qualitative feature I just want to point out here is that goes to 0 at erasure probability 1/2, right? So that gives, there's still something non-trivial happening with this channel, but apparently it's too noisy to actually be of any use for sending quantum information over it. It's just any erasure probability beyond 1/2, the quantum capacity is 0. Okay, so that's our whirlwind tour of quantum channels and their capacities. Now I want to look a little bit about how additivity and non-additivity show up, even with the quantum erasure channel that we'll see. So as I said, additivity means trivial interactions, non-additivity means non-trivial interactions. They're both, if you can get one or the other, you should be happy. There's a lot more to understand in terms of non-additivity though. So one thing I wanted to say, well, the coherent information, sometimes it is actually the right answer for the quantum channel capacity. It's specifically the right answer for what we call degradable channels. What's a degradable channel? It's a channel where if you have the output of the channel, you can always further degrade that output to get the environment's view of the channel, to get the complementary channel. So, and those channels have additive coherent information, and that means that the quantum capacity of channels that are degradable is just given by the single letter coherent information. And basically, you should think of degradable channels as being channels where the receiver has like strictly more information from the input than the environment gets. And you can see that by if the receiver adds even more noise to its output, then it can mimic the environment. So there's nothing that goes to the environment that is not also understood fully by the receiver. So this is, this offers some lessons for us. The first is, well, random coding is not so bad. It's actually gives us the capacity for some small class of channels. Non-additivity of the coherent information is somehow connected to the information that's getting sent to the environment. There are examples of non-additive channels with non-additive coherent information. They're never degradable, and understanding them better will require us, I think, to put the environment of the channel in a more sort of equal footing with the receiver of the channel. And the third lesson is that, well, most channels aren't actually degradable. Most of the time, like if you take a generic channel, it's just not going to be degradable. And that's because actually, in fact, degradability is extremely fragile. So if you take a degradable channel and perturb it a little bit, it probably won't be degradable anymore. If you compose two degradable channels anymore, it's no longer degradable. And the composition of two degradable channels actually gives some of the simplest examples of non-additivity of coherent information. Approximate additivity is possible. So if you have a channel that's sort of approximately degradable. So what does that mean? It means if the output can, in some way, approximate the environment of the channel with good approximation parameter, then the quantum capacity of that channel is going to be close to the single letter coherent information. And this is good, for example, for low noise channels that are approximately equal to the identity. Very little information in those channels gets leaked to the environment. And that means that such low noise channels are approximately degradable. And that lets us show that the coherent information is, up to small corrections, a good expression for the quantum capacity. And it gives us optimal codes, right? Because we get, if the coherent information is equal to the capacity, it not only comes with, a numerical value that tells you the capacity, it comes with a recipe for generating good codes that achieve that capacity. So at least in some cases, again, coherent information is the right way to think about the quantum capacity, specifically for the ones that look like, that are either degradable or very close to degradable. Now, non-additivity of coherent information, it happens in many different kinds of examples. And basically, what does it mean? It means that, well, the coherent information for a single use of the channel, it's achieved for a randomly chosen code. And what non-additivity of coherent information tells us is that you can do better by than random coding by picking more structured codes. And specifically, if I have some state on many uses of the channel, and the coherent information of that state is strictly bigger than n times the coherent information of the single use of the channel, then by building codes that are structured sort of like that reference state, you can achieve higher communication rates. And what we would like is, we want to know, given some channel, what kind of structure should good codes for that noise process have? And ideally, we'd like some sort of compact prescription for generating the capacity and achieving the codes in terms of typical sequences, entropies, and such. We're not there yet in terms of quantum capacities. Where we are right now is more of a butterfly collecting point, where we're looking for examples of non-additivities that can help illustrate what causes the non-additivity and when is non-additivity strongest and most useful for quantum communication. So where we sit at the moment is sort of looking for examples of channels. And basically, if the rule of thumb for non-additivity of coherent information is that if you have a channel that's pretty noisy, then you're probably going to see some non-additivity of coherent information. I just see I'm putting my hand up. I don't know, just recently, I think Zoom started putting your hand, like if you put your hand up in the picture, you'll put your hand up as an icon there. It's pretty amazing what they can do with this artificial intelligence these days. Anyway, so non-additivity you get for depolarizing channels, poly channels. One of my favorite channels, it's called the rocket channel. We won't talk too much about it today, but it's a sort of a large dimensional random unitary based channel. We can actually see these non-additivities only appearing for large N. You can find examples of non-additivity for Gaussian channels. They're basically, wherever you look, you typically can find some non-additivity if you're in a pretty noisy setting. I'm trying to figure out how to put my hand down. I think I can do it like this. There, I just told it to stop recognizing my hand gestures. I'm sorry about this delay. And
I have got an option to do that too.
Yeah, okay, good. Turned it off. Okay, so long story short, this non-additivity is more or less generic for very noisy channels. And what we want is to find a more systematic way of understanding it. To date, what we have is an understanding that that something's going on here and we need to understand it better. So that gives us a lot of open questions and also a lot of possibilities for using new techniques to answer those open questions. So let me tell you about one of my favorite channels. We call it the platypus channel, and it gives non-additivity of coherent information for this channel together with an erasure channel. So two very simple channels. What does this channel do? Well, it takes a 0 and it maps into a maximally mixed state between 0 and 1. And then if you put a 1 in, it gives the receiver a 2. Okay, this is actually a degradable channel. I'll leave that as an exercise. That means it has additive coherent information. And furthermore, the coherent information together with the erasure channel, which is also degradable, is additive. So there's no non-additivity. What I want to add a little wrinkle to this very simple channel, and we're going to make that degradability break, and we're also going to make the additivity break. We're going to add one more state. And what does the state do? Well, you can put in a 2, and then at the receiver, they just get a 2. So it doesn't do anything different from putting in a 1 from the receiver's point of view. But at the environment, if you put in a 1, the environment gets a 1. If you put in a 2, the environment gets a 0. Okay, so the environment of this thing is now, it's still a qubit. The output of this thing is a trit. And there's this seemingly useless extra input at the input that, well, it lets you send a 2 to the receiver in 2 different ways. This has some nice properties and some apparent, some inconsistent seeming properties and some very simple things and some very complicated things about it. That's why that's one reason we call it the platypus channel. It's also sort of constructed by like stitching together a bunch of two different channels. This is like a really simple channel to the environment. This is like a really simple channel to just the top two to the receiver. And when you stitch those together in just the right way, the whole that you get is not nearly as simple as the individual things you stitch together. So what are some properties? Well, we can calculate lots of capacities. We can calculate the classical capacity. It's 1. You can probably see how to achieve 1 too, right? Like if you want to send a 0, use 0. If you want to send a 1, use 1. And then the receiver will either get the 0, 1 space, in which case they know you send a 0, or the 2 space, in which case they know you send a 1. So the classical capacity is 1. In fact, you can do that privately. The private capacity is 1. That's true also for the complementary channel. You can send exactly 1. Oh, okay. You can send exactly 1 bit to the environment and no more. And you can do that privately as well. However, this coherent information of this channel can display a non-additivity when used together with an erasure channel. And that non-additivity is not of the usual form that we typically see when we see examples of non-additivities together with erasure channels. Also, it has the property that you don't really need to use an erasure channel. This channel, you can use, basically take any noisy channel you can think of. Typically generically what happens is, if it's not degradable, this channel is going to kind of be able to generate non-additive coherent information together with that channel. It seems to be kind of a universal non-additivity or helper channel that can be that doesn't depend very strongly on what the channel is you're using it with. And finally, you get a non-additivity of this coherent information even far away from where the coherent information is 0. And I said before, rule of thumb, you have a very noisy channel, you're going to get non-additivity. This is an example where it's not too noisy and you still get non-additivity and it's still pretty generic. So this is, for me, one of the places that I've been looking at recently to try to get a better handle on non-additivity of coherent information. Okay, so I said non-additivity, it's about quantum resources interacting non-trivially. We look for these examples because we're trying to work because the cleaner the examples that we can find, the easier they should be to understand, and the better hope we have of working towards some general theory of coding strategies that take non-additivity into account. And there are features of this platypus channel that point towards a more environmentally focused approach to the quantum capacity. And I think that's what we need, a more explicit inclusion of the environment in our consideration of how our coding strategies work. So looking at these examples, it's about looking for a handle on how we should generate new recipes for doing good error correcting codes. And the goal here, always in the back of our mind, is to find coding strategies that are achievable, that go beyond the coherent information. And I would be delighted, and I think one of the outstanding questions in this area is to find some single letter formula that's achievable and exceeds the coherent information in at least some cases. We don't yet know that. So actually, I said the quantum capacity is more complicated than the classical one, and it certainly is. This picture of the erasure channel over here, capacities, shows you that even at erasure probability of 1/2, where there's plenty of classical capacity, so there's plenty of correlation between input and output, there's still 0 quantum capacity. And we think of that as kind of the coming from the delicacy of quantum information. There are lots of ways to have a totally terrible quantum channel. There are lots of ways for a quantum channel to have 0 quantum capacity. There's actually only one way for a classical channel to be totally useless, and that's for there to be no correlation between input and output. So here's the classical 0 capacity channel. It's the only example. And of course, if you have 2 of these, it's not any help to you either. But the quantum channel, there are different ways for it to have 0 quantum capacity. And because of those differences, you can ask yourself, what happens if I take 2 channels that have 0 quantum capacity, but for very different reasons? What kinds of reasons could they be? Roughly speaking, an erasure channel is kind of like a lossy channel. You're losing part of the signal to the environment, whereas other kinds of channels are more like noisy channels. The power of the signal doesn't change. You just are adding extra noise to the thing. And where we find interesting non-additivities is where we try to combine those 2 sort of very noisy and very lossy channels when we put them together. So before we look at that non-additivity, I want to give you an example of a quantum channel that you can calculate the quantum capacity for. And to do that, we're going to look at the no cloning theorem. So the no cloning theorem, it just tells us, well, there's no physical operation that takes an unknown quantum state psi and maps it to psi tensor psi. Why? Well, it's not linear. Okay, and even like, look, this is quadratic in some ways, right? I've multiplied this psi by itself. And even in sort of more finer detail, we see that the more information that you leak about your state to an environment, the more it corrupts the intended state that's supposed to go through. And this no cloning, to me, is at the heart of how classical and quantum information are different. Classical information can be copied. Quantum information cannot. And that's kind of a lot of quantum information theory follows from that. And a lot of the differences follow from that. So let's look at a 0 quantum capacity channel. It's called a symmetric channel. And the 50% attenuation channel or 50% erasure channel will be an example of one of these. So a symmetric channel is just one where if the output is symmetric where the output of the channel is symmetric between the environment and the receiver. So that means if I take the unitary of the channel, or Stein spring dilation, I think they call it, and swap the receiver and the output, I get the same thing back again. Okay, so the receiver and the receiver and the environment get exactly the same message. Okay, so let's see why that should have 0 quantum capacity. Well, suppose I have a symmetric channel. Now that means I can just swap B and E and I get the same thing back again. Well, also let's suppose I had some positive quantum capacity. Well, that means I'm allowed to use many uses of my symmetric channel. I'm allowed to do an encoding and a decoding. And if I have some non-zero quantum capacity, I can take at least a qubit and encode it, feed it into the channel, and at the receiver, do the decoding and get the state back out again. Great, that's what it means to have quantum capacity. But remember, this thing is symmetric, which means this thing is symmetric if I swap the E's and the B's, which means if I do the decoding on the B system and get the state out, I can also decode on the E systems and get the state out. And now I'm in trouble because I've cloned my input state. So the assumption that this channel is symmetric and has positive quantum capacity, non-zero quantum capacity, has led us to a contradiction, has led us to a violation of no cloning. No cloning isn't violated, no cloning is true, and that means our assumption that was wrong was that we had a positive quantum capacity. It's got to have a zero quantum capacity. And actually, all known zero quantum capacity channels have a reason like this for having zero capacity. The second kind of channel, the not symmetric ones, are the reason that they have zero quantum capacity is that they have positive partial transpose. They can only make positive partial transpose states. And that means, you know, the fact that they have zero quantum capacity comes from the fact that transpose itself is a positive operator, but it's not a completely positive operator. So it's not a physical operation. And having quantum capacity for those PPT channels would give us violations of the non-physicality of the transpose map. So this is just to remind you, there are these two kinds of zero quantum capacity channel, the symmetric ones, like 50% erasure channel. We saw why the quantum channel capacity is zero for those. There are also these positive partial transpose channels. I just said that they have zero quantum capacity, but they do, and there's a whole theory of it. We're just going to take examples of those, and what you can do is you can find pairs of channels, which, you know, one of which is PPT but not symmetric, the other is symmetric but not PPT, and they both have zero quantum capacity for their respective reasons. And then when you take the tensor product of the two things, they have some positive quantum capacity. Basically, the reason for each one of them having zero quantum capacity disappears when you put the two things together. And when we first found this, we thought this was like kind of a cute curiosity. But what we've learned in the years since is actually it's pretty darn generic. So like if you have a zero quantum capacity channel, chances are you're going to be able to find a partner for it that has this super activation effect that you can put with it, that gives a non-additivity of the quantum capacity in this very strong way that takes two zero quantum capacity channels and makes the joint channel have non-zero quantum capacity. And in fact, this has been realized experimentally in some optical experiments, and people have shown that you could actually generate more coherent information by using the appropriate two-channel input states than you could with single-channel input states. Okay, and this leads to an interesting idea that I really like, which is these symmetric channels, they have zero quantum capacity. Since they have zero quantum capacity, let's throw them in. Let's say if you have a quantum channel you're interested in using, let's ask ourselves a new question. The new question is, if I have access to arbitrary symmetric channels, they all have zero quantum capacity, but I can use them in any way I like together with the channel I'm interested in, and what's the capacity in that setting? We already saw that in some cases, the capacity can be increased over the quantum capacity. It can go from having zero quantum capacity to positive assisted quantum capacity. But the beautiful thing that this does by throwing in this extra resource is that it gives a nice, simple formula for this symmetric side channels, we call it, symmetric side channel assisted quantum capacity. That is given by a single letter formula, which just is the evaluation of a coherent information of your channel N together with a universal symmetric channel, just an infinite dimensional channel that's symmetric and therefore has zero quantum capacity. So this has some great features. First of all, it's additive, it's single letter, and it has a bad feature. A priori, we don't know any bound on the dimensions of the auxiliary systems of the state that we're optimizing over. And that's the sort of thing that happens also with the squashed entanglement of Christandl and Winter, where they also see that by throwing in, there seems to be a trade-off of complication. If you want an additive formula, you can sometimes get one, but if you have an additive formula, sometimes the additivity of the thing makes it hard to evaluate, even though the reason you wanted it to be additive was that you hoped it might simplify things. So let's just summarize what I've told you about additivity and non-additivity. Additivity, it tells us we're on the right track with random coding when we find additivity for some classes of channels. Non-additivity tells us we're missing some key ideas about how to generate good structured codes for quantum communication. Initially, the examples that we had of this were kind of complicated, either to analyze or to construct, and that obscures what's happening. And increasingly, we've been finding simpler examples that point towards new strategies with maybe a more explicit role for the environmental information. And I think this is a place where things are really ripe for progress in better understanding coding strategies based on these simpler examples. And I focused on the coherent information, as I said, and the quantum capacity, but there's a similar story for classical capacity, private capacity, et cetera. So now let me show you an example, kind of change gears a little bit, and show you an example of two different resources. One of them is classical, one of them is quantum, and show you how you can boost the classical resource by using this quantum entanglement in a network setting. So the simplest classical network maybe I can think of is called the multiple access channel. It's got two senders and one receiver, sort of like two cell phones are trying to, the uplink in a quantum cell network. You have these two cell phones and they're trying to both talk to the tower at the same time. And there's just this one receiver, and maybe the signal from this one would interfere with the signal from that one. And you can characterize the performance of a classical, this is all classical so far, the classical channel. You can characterize its behavior in terms of some conditional probability distribution of output Z given inputs A and B. And our goal is to basically find out what are the rate pairs that we can achieve. What are the pairs of communication rate from sender 1 and sender 2 that we can simultaneously achieve over a given multiple access channel. This is like the canonical solved classical information theory problem. This is the canonical solved classical network information theory problem. There's what we could think of as a single letter formula for this quantum this capacity region of the multiple access channel. It was found in the 70s by Alzveda and Liao. It's just, you can learn about it in the Cover and Thomas textbook. And it's really beautiful. But what we want to look at now is what happens when we add entanglement between the two senders. So in the totally standard classical case, they might have some shared randomness. It's a classical channel, so you might say, well, what good is sharing entanglement between the senders? The first thing they're going to have to do is just measure it to find some classical message to feed into the thing. So maybe it's not going to help at all. What we found actually is that in contrast to the one sender, one receiver case, that entanglement can boost the classical capacity of this multiple access channel. And it does so even for this utterly classical task of sending classical information over a classical channel from two senders to a single receiver. And certainly for a single sender and a single receiver, entanglement does not help in that case. And what we found is at least examples of, you can see this is the capacity region of a channel we built based on the magic square game of Merman. And you can see this dot here is an achievable rate that you can achieve by sharing entanglement between the two senders. So you can actually do strictly better than you could classically by sharing entanglement between the two classical senders. And actually even better than this, you can show based on this sort of mapping, based on sort of fitting some non-local game into a multiple access channel, you can show that that approximating the capacity region of a classical channel, forgetting about any kind of entanglement stuff, you can just cook up classical channels that embed a hard computational problem into them in such a way that if you want to calculate the capacity region to better than 1 over cubic in the input alphabet size, that's an NP hard problem. Even though this formula is totally simple, classical single letter formula. So it's an example of, it sort of problematizes the idea of that single letter formulas are sufficient to give a solution to an information theoretic problem, because there are problems like the multiple access channel capacity region that does admit a single letter formula, but it's still computationally intractable to solve. With that, I want to just thank you and say, there's all sorts, I talked about some topics way up here in quantum information theory about like the sort of fundamental topics in the theory of basically Shannon theory, looking at capacities, superactivation, quantum networks, correlation measures a little bit. And all of those, provide the kind of the foundations for more applied studies that I'm also very, very interested in applying to sort of more fundamental, or sorry, more traditional areas of physics. I'm particularly interested in being at a place that's basically a metrology institute in understanding fundamental limits on metrology. And many of the mathematical tools that we developed to understand quantum information theory also have applications there. Oh, I did not want to include this magnetic field sensing thing because I'm just about out of time. So I will summarize and say, well, capacities, we want to study them because they tell us the value of a noisy quantum resource, the best rate we can achieve over a quantum channel, the best performance of quantum error correcting codes that we could help for. And we saw that, that the interaction between many different quantum resources can be non-additive, more like baking bread than making a smoothie. And we even saw superactivation where two apparently useless things, zero quantum capacity channels, can work together to get positive quantum capacity. This non-additivity is a challenge because it makes it hard to evaluate capacities, but it's also an opportunity because it offers the possibility of finding better recipes and new effects that aren't even really imaginable in the classical theory. And I showed you also in a specific example of two very different resources that we could make interact in a fruitful way, a classical multiple access channel and entanglement. And I showed how to use a specific non-trivial interaction to accomplish a totally classical task better by using quantum entanglement. And with that, I want to say thank you so much. And I look forward to any questions you have.
Thank you very much, Dr. Smith. So it's time for question. If anybody has any question, please go ahead.
I have a naive question, sir.
Yeah, please go ahead.
So whenever we calculate the channel capacity, first we encode the information and after transferring through the quantum channel, we decode it. But after decoding, somehow the state is slightly different from the input state. That means there is some error probability in the output state. So my question is, how much error probability is allowable and how to quantify that?
Oh, sure. So typically what we find, okay, I can say more about classical and quantum, but basically our goal is to make an arbitrarily small error. And typically what you find in the classical setting is that you can get exponentially small error. So what you do is you say, hey, for any rate strictly less than the capacity, I can get an exponentially small probability of error by using bigger and bigger codes. And you know, the exponent the coefficient in the exponent depends on how much smaller than the capacity you've chosen to be. And finding similar answers or similar, what we know in the quantum setting is that we cannot approach, up to the capacity we can approach fidelity 1, and above the capacity we cannot approach fidelity 1. However, we don't know as well whether we can get exponentially shrinking errors in the quantum setting.
Okay.
Okay, any more question? Do we have?
Can I ask a question?
Yeah.
Please go ahead.
Thank you for your talk. In understanding whether quantum channel is additive, superadditive, or subadditive, one has to calculate quantum capacity of the channel. So my question is, are there any recipes to reduce or optimize number infinity to some reasonable number of copies of a channel? Otherwise, when copies grow to infinity, then it is hard to calculate on the computer. Moreover, when size of the density matrix increases, then it requires more hardware computer resources.
Mm-hmm. Yeah, that's absolutely right. That it is a hard thing to do. And with a limited set, well, basically there are special classes where we can do the optimization. Either we get an additivity of the coherent information. Actually, we basically do need to have additivity of coherent information. And in that case, we can just evaluate on a single letter. However, in general, we don't have any recipes for doing that calculation. What we have are upper bounds. There are sometimes, well, there are upper bounds on quantum capacities that we can evaluate sometimes efficiently. But those aren't always tight in the sense that like they might be very, very much larger than the quantum capacity. So it's not that if you give me a channel, I can calculate what the quantum capacity is. It's still an open question. And part of, well, that one of the goals in trying to find simpler characterizations of quantum capacities is to try to enable us to actually calculate what the quantum capacity of, you know, an arbitrary channel is. But right now we don't have a good handle on that.
Thank you.
So any more question? I think we are almost about time.
Thank you very much. It's been a lot of fun.
Yeah, thank you very much, Dr. Smith, for that insightful talk. Very interesting. So I think we exactly finished in time. Yes, yes, Dr. Panigrahi.
No, I'm just thanking you. Thanking you. That's all. Thank you. Yeah.
Thanks.
Thank you very much, Dr. Smith.
Yeah. Ghosh from